As some of you have noticed, the website's down at the moment. It crashed. We tried to fix it. It got worse. We're reinstalling. Everything should be back later this afternoon. Sorry about that. So this is the little bit about mid-semester grades. People have been asking about it. So here's how we calculated the mid-semester grades. We took the best 3 assignments. Okay. We took the best 4 quizzes, but we weight the assignments more than the quizzes. We took the midterm exam at 40%. We did not grade anything with respect to the project because you're all doing so well in your project and you've got things so nearly working that we decided that we wouldn't actually give you a grade. Okay. One of the things we do in natural language processing is trying to detect sarcasm. Okay, so that previous sentence might have had something to do. No, we just didn't grade that. You all can work harder on your project, and it will be an important part of the final grade. But we've not included that in the mid-semester grade because we didn't even have the meetings with you until we after we made that grade. My observation of the distribution of scores is that the assignment scores are really, really valuable, okay? They're the ones that sort of make the differentiation, okay? If you look at the distribution just of the midterm exam and you look at the distribution of the assignments, the distribution of the assignments are really important. That's how you get more grades. So homeworks are important. I'm not saying you should blow off the exam, okay, because you've got to be far too brave, actually foolhardy to do that. But the assignments are pretty important. Likewise, the project's pretty important, so don't think that that's just some extra thing and you'll make it up on the exam. So yes, you can get, and you should care about the exam, but the other things are probably giving you more bang for your buck, so it's probably worthwhile really caring about those. Okay, distribution is 5 A's, 34 B's, so slightly more A's than B's. The number of C's is sort of hard to calculate because there's some people who don't actually have a mid-semester grade yet for various reasons. There was about 8, I think, in the C space. But the list I looked at wasn't exactly sure who are the ones that sort of don't really have a grade yet. You're all doing fine. B's are good. Okay, I know you all want A's, but B's are fine too. Do care about the assignments because that's where you can make your most. And that's, if you miss an assignment, you don't have enough assignments, it really costs you. Okay?
So you're saying the midterm exams have been graded?
The midterm exams have been graded.
Oh.
Yeah, we graded them the day after you did them.
So how do we see?
Oh, right. Okay. So if you go and speak to the TAs, you can go and see your actual grade and results. We do not return the exam to you. We are planning a session where we're going to go through some of the aspects of the midterm, but we're not going to do that until everybody's done it, which will be early next week, and then we'll actually go through it. Yeah.
Do you know if the grades will be on Canvas? You said they weren't returned. The tests themselves weren't returned. But will the grades be on Canvas?
We can post this. You mean more than that? You mean what your grade was? I mean, you got your mid-semester grade. You want your individual exam grade.
Yeah, I think that would be helpful.
Okay. Okay.
Is it on Canvas already?
Are these grades on Canvas?
I don't know if they're on Canvas, but they're all within the same spreadsheet that we're putting the other grades on, and I think that if somebody can tell me, yes. So this week we're continuing our descriptions of semantics, and today we're talking about really into computational semantics and particularly semantic parsing. So before, when we were talking about meaning representation languages, we were talking about them the abstract. It was like, this is what we want. Now the answer is, so can we actually get it from syntax? Can we actually get it from the text? And the answer is, yeah, sort of, but it's hard, because the relationship between surface level sentences and some internal semantics is unfortunately harder than what is immediately obvious. But we can still often do it well enough for particular tasks that it's certainly worthwhile, so it allows us to do it. So it's really what we're talking about today. We're going to actually present particular meaning representation language, and then we're going to talk about how to be able to relate that to actual syntax. Okay, so we're really looking at the relationship between syntax and natural language sentences and the semantics. So that's the thing that we're trying to do today. Okay. One of the things you should remember about human conversation, human generation of language, is there's a phenomenal amount of background information that people don't talk about when they're actually saying things. Because we have this shared perception of what the world is like, what the words actually mean, how we describe things, what should get mentioned and what shouldn't. If we do mention something, we assume it's important and differentiable from the rest of the world. We don't just add information for the sake of information when we're actually talking. We actually say things because we have a purpose, because we actually want to highlight the things that we're actually talking about. And so we do not say everything that's true when we're actually giving information. So there's an awful lot of hidden information. Okay. Now, those of you who are non-native and therefore much more aware of how English gets used in such a way that you think, what the hell are they talking about? When they use metaphors, when they refer to things which you just don't have enough background to how to do it. So I'm going to give an example of this. Occasionally I'll watch some video about EVE Online. Does anybody know what EVE Online is? It's a video game where they play with spaceships and it has a whole economy type thing. It's all in English, and you watch a video that describes what's going on in an EVE Online game, and the answer is, I haven't got a clue what is going on. I mean, none of the words mean anything. I mean, I can tell you the words, I can tell you what's being said, but I just don't know what they refer to, because they're in an environment that I'm unaware of. I don't play the game, and so I don't know what the names of the ships are. I don't know what the good guys and the bad guys are. I don't know what the special vocabulary is. I don't know what a big ship, a small ship. I just don't know. And so it's incredibly hard to understand, even though it's in English. Okay? And this is what a computer is like. A computer deals with these strings of words that come in, and it's like, well, I know what these words might mean in this context, but I don't know what's not being said. So you have to understand that there's more than just the words when you're actually trying to work at the meanings. Okay? And we assume this background knowledge all the time, and it's incredibly hard for computers to actually care about this. Okay? We would like to be able to care about things like grading assignments automatically, restaurant menus. How do you understand a restaurant menu? In fact, that's actually quite a good example as well, where you might know lots of words in English and you go and look at a restaurant menu and it uses all these words that you don't really know what they mean because they're French or they're pseudo-French, they're not really French. Okay, they want to appear French. And you have to think, well, what is this? And so you have to ask the wait person to actually explain things to you, or you can just say, oh, I'll take the fish, hoping that there is fish on the menu and you don't look stupid. I do that all the time. So you don't know what these things are, although you can often work out, well, that's probably some type of meat that I don't know, and that's probably some type of sauce, from the context that you can actually work that out. Okay? Likewise, when you're learning to use a new piece of software, there's instructions, they tell you what to type, you don't really know the space of things that you can actually do in it, but you know that it's quite likely, okay, so they give you a new programming language that you have to learn, so you start using it, and then about halfway through you think, okay, I don't know how to do the syntax of else in the if, I don't know if I'm supposed to bracket it or not bracket it, and so you go to Stack Overflow, because where else would you go? You look it up and you try and find an example of the thing, and then you learn it. You know what you're looking for, but you just don't know the fundamental syntax of what's actually allowed in the particular language, whether it's got an elif, or you have to say else if, or you just have to say else space if. And so you don't know, and you want to go and find out what it is. Machines are stupid. They don't have this information. They're not quite good enough yet when they get stuck to go and post on Stack Overflow to find out what the answer is, I think. Well, that would be interesting. So in other words, the information that's actually in the sentence that you're looking at probably isn't enough to work out what's going on. Okay. Now, there are special cases of sentences when it is, but they're sort of a little weird, that have a very clear semantics. What's the weather in Pittsburgh tomorrow morning? It's got all the information in it, although it doesn't really know what weather means. It just knows that it has to look up some number from Pittsburgh for tomorrow morning. We talked about meaning representation languages, various forms of logic. There's usually some symbolic representation, although there might be some continuous space, I suppose, nowadays with neural nets, but it's still the same concept. We have a representation which supposedly means something. Okay? We're usually talking about converting a sentence, and we don't mean it in the strictest sense of a sentence, some relatively short bit of text, into some representation, and we take all of these sentences, and what we say is, this is a model of the real world. Okay? Now, it's not really a model of the real world. It misses an awful lot about the real world, but it should be sufficient in order for us to do the task that we're actually doing, which might be ordering something in a restaurant, finding the time the next bus, caring about weather, maybe solving logic puzzles if it's something like that, maybe grading an essay, but it doesn't really need to understand everything about the world. Okay, we're going to use first order predicate logic as we talked about earlier this week because it's relatively well defined, even though it has problems around the edges, but all logics actually do. But we're going to use it because as things go, it's pretty well defined. Okay. So we sort of talked about this bit before. What do we want in a meaning representation language? We would like to be able to query against the knowledge base and know whether something's true or not. So we have some set of data. I showed some paper bag. It's a knowledge base. We're going to ask about the content of that bag, and we want to be able to get yes and no back. So we're going to ask questions, okay, which give back yes or no answers. Are they true or false? Okay. Do CMU students follow politics? Okay, and so we have to know that whether students follow politics or not, or at least know whether some students follow politics. Okay, we'd like to eliminate ambiguity so that if there are multiple ways of interpreting something, we want to find the one that's appropriate, the one that's meant by the actual sentence. CMU students enjoy visiting senators. Does that mean the students go to the senators, or they enjoy the senators that are visiting us? There's an ambiguity in there. Okay. We like to be able to cope with vagueness. Okay, Sally heard the news. We don't know what news that is. If we're in a concept last Saturday when we had tragic news, you didn't have to say what it was. You could just refer to it indirectly as, have you heard the news? And people knew what they were talking about, or didn't, because they hadn't heard the news. Okay, so the news might just be, did you see the 6 o'clock news? Do they still have 6 o'clock news on TV? So did you see the 6 o'clock news? Or it just might a specific event that you're actually asking about. Okay? And it's unclear. And maybe you need to define what it actually is. You want to deal with this canonical forms. There are multiple ways of saying the same thing. You would like to be able to get a representation that does it no matter what actually somebody says. And you'd like to be able to do some sort of inference. So draw conclusions based on the knowledge base. Who became, see this slide's old, who became the 45th president. So you'd like to be able to make inferences about the information as well. Okay. Model theoretic semantics is a particular form of philosophical logic about representing the world. The model, okay, people have different definitions of this because I've been in multiple fields and they all are utterly sure that they know what it means and they're all utterly different. So that's exactly the ambiguity. Model is the list of facts that you actually have. It's a simplified representation of the real world. It is not the real world. Okay, so if you edit IMDb to be able to add your own name into a star of the movie Star Wars, it doesn't actually make you be a star in the movie Star Wars. Okay, it doesn't change the world. Okay, it's just a representation of the world. Okay, and you have to be aware of that distinction. And you probably want your database to represent some part of the real world because you're expecting to do it. But maybe not, because maybe it's a video game thing that you're doing, and therefore there isn't a real world. But there's still a video game world, but you want to make sure that the representations are actually there. Okay? Each element, each noun denotes a well-defined part of the model. So typically you'll have words that refer to particular objects. That particular mapping is called an interpretation. So you have this database and you say in IMDb that my symbol for Harrison Ford means the actual Harrison Ford character in the real world. That's what it means. Okay? And where you have actors that have the same name, 1, 2, and 3, you want to make sure that the one goes to the 1 and 1 goes to 2, 1 goes to 3. The actual physical character in the real world. So this is an interpretation. You've got all these facts in your little brown bag, and you want to talk about their interpretation in the world that you're dealing with, and so you want to be able to evaluate to actually find these characters and what the representations actually are. And you'd like that to remain true to the world that you're trying to model. Otherwise, there's sort of not a point in doing it. So a particular model, so here's a particular model that we're going to talk about over the next couple of slides. We can have a domain, and so what we can do is have all of the different symbols that we're actually going to deal with it. We have a bunch of people, we have a bunch of restaurants, okay, and we have a bunch of different cuisines. We can have properties. These properties are going to relate to particular objects in the domain. So we can have properties like crowded, we can have expensive, we can have cheap, we can have good, we can have bad, and so we can define what these actually are. We can have a bunch of relations, so we can say likes, and we can say some human, that's the first argument, and some restaurant is the second. Okay, these are all still written in natural language, but you can see they have a direct representation in first order predicate logic. So we can actually do that. So what we can do is you can say, okay, let's take all the objects, the people that we want to refer to, and let's actually give them some symbol representation. Let's at least make them letter related so it's easier for us to understand. The computer doesn't care. They can be called G1 to G34. It doesn't really matter. We have the definition of which things are crowded, the definitions of which things are expensive, the definition of relations of likes, the definitions of serves. So we've got that information. Okay, there's lots of different subtle ways of representing that information, but they can all be topologically the same, isomorphic representations. We're talking of relationships between objects within our domain. We're naming what these objects actually are. So we can end up with English, like Karen likes green mango and Frederick likes Casbah. And what we can say is we can make those facts about the world and we can translate them into this representation. Okay, Noah and Rebecca like the same restaurants. Okay, that's sort of derived from the distribution of information. You have to go and see all the ones that Noah likes, all the ones that Rebecca likes. Noah likes expensive restaurants, and not everybody likes green mango. And so you can say these English things about the information that we actually have. Okay, so even though we've got this internal representation, there can be lots of interesting things we can do in the natural language end that are not just adding information into the database. We can say whether these things are true, or we can even derive things from the set of descriptions that we have that would be true about it and present them as natural language. Okay. This type of semantics is usually called truth conditional semantics. We're talking about a representation that is true of the world that we're talking about, and we're talking about these sentences being true or false or derivable from the information that's actually in that data set. even in first order predicate logic, it is possible that there are some things that you can derive, or some things that are true about the world, but you can't actually derive from the data. So they can be relatively complex things, and I'll touch on that later. So first order predicate logic is a particular form of logic. The reason it's called first order predicate logic is because you can only quantify over variables that refer to the domain objects, and you cannot quantify over relations and predicates. That would be a second order logic. Okay, so the terms in the domain, what we call the domain, so this is like Noah, Rebecca, Frederick, etc. These are the things that we can quantify over. Okay. Predicates give information about sets and relations, so they are giving predicates, they've got arguments, they then can be true about something. And we've got a bunch of logical connectives. We've got and, which is usually written as this symbol, or we have not, that's written in this, and we have implies. Implies is actually the same as, so A implies B is the same as not A or B. It takes a while to work that out in your brain, but it's actually the same. So this is only a sort of syntactic addition. You don't actually need it to be able to describe the same things. Also in first order predicate logic, we have these things called quantifiers. I'm going to spend a little bit of time on quantifiers because they're a little weird. Natural language has quantifiers as well, and I'm going to spend a little time explaining to you about quantifiers because they're subtly weird. Okay. There are two ways to use variables. Okay, we have two quantifiers, so we use this quantifier with respect to a variable. One is called existential, and it's usually written as an upside down E. It's not a number 3, though it sort of looks like a number 3, but it isn't. We usually read it as that exists. And what that does say, that if I say that exists X, I mean there has to be at least one valid value for this within this expression in order to make this expression true. There can be multiple possible values, so there has to be at least one. The second quantifier is called the universal quantifier. It's usually read as for all. It's written as an upside down A, okay, for all. And it's used to be able to say that every single possible value that I can put in for X, okay, the statement is going to be true. Okay, and these two, that exists and for all, are the only ones that are allowed in first order predicate logic. There are other quantifiers that we can have, but they're not in first order predicate logic. So for example, if we have a sentence like a restaurant near CMU that serves Indian food, what we can do is we can represent that as there exists X, which is a restaurant, it's near CMU, and it serves Indian food. Okay? And is this true for the real world?
No.
Why?
Because there's no restaurant near CMU that serves Indian food.
So it depends on one's definition of Indian and food and near. Okay? Is Craig Street still near CMU?
Oh yeah, there is a
But maybe you want to go up to Tamarind before you have a real Indian restaurant, which is a valid, so we actually still do need to care about what these things really mean. Do we mean the trucks? Do the trucks count as restaurants? Maybe. So we have to have some definition of that. Okay. Then we have the next one. All expensive restaurants are far from campus. Okay. And so we have a for all. So for everything that's a restaurant and it's expensive, that implies that it's not near CMU. Okay? So is this true for the real world?
I mean, Lucas is kind of expensive.
I agree.
I don't know why.
I don't know why it's so expensive. It's so we can pretend to go to an expensive restaurant, but we don't have to go very far to do it.
Yeah.
It also depends on your definition of expensive and near. Okay, so there are some things that are more expensive than others, even on campus, and we think, it's more expensive than I want to pay. So it depends on your definition of that. But this is what this sentence means in first order predicate logic. we'd have to have a database of definitions of restaurants' expensiveness, okay, and locality with respect to CMU in order to actually answer this with respect to this sentence and this information. And it doesn't necessarily reflect what real humans would think about the particular restaurant or whether they think it's expensive or not. We're going to add a further extension to first order predicate logic. It's called lambda notation. If you've done certain programming languages and certain types of programming, you're going to find this very familiar. It falls into this thing called category theory. It's very useful for doing representations of partial pieces of natural language, which of course is going to be useful when we're trying to do parsing and trying to get a representation of part of a sentence. And we'd like to get a representation of part of a sentence. And what we do is we basically say we can have lambda x where x appears somewhere as a free variable within the expression. Okay? Some of you might think that's just a function. Yes, you're right, it is just a function. Okay? But I don't know which one came first. It's a particular logical form that people developed in order to be able to represent incomplete logical expressions with what's called free variables, and so that they can actually be bound with a lambda x at the beginning. Okay, so for example, we can have an expression saying lambda x, and we can say near x CMU, and that's a valid logical expression, even though it's got this x that doesn't have a value in it. Okay. What we can do, though, is there's a thing we can do is we can take a lambda expression and apply it to a particular value so that we can actually reduce it in some form. So if we've got this expression, lambda x near x CMU, and we apply it to Lulu's noodles, what we can get is near Lulu's noodles CMU. And this is actually just a syntactic manipulation. Okay, these two expressions mean exactly the same thing, okay, but this one's sort of easier to read, okay, but that's all, okay. They mean exactly the same thing. Technically, you don't need to do it, but yeah, you do if you actually want to do it, because then you can look this up in a database. Well, this is a little weird, and you want to simplify it first, okay. So in the same way that 2 plus 2 means exactly the same thing as 4, it really doesn't mean anything different than 4. Okay, and that's what the equal sign means. But 4 is sort of the answer. When people say, what's 2 plus 2? Apparently you're not allowed to answer 2 plus 2, even though that's completely true. But that's not the expectation. You want the simplified version of it, even though they mean exactly the same thing. Inference is something you can do with first order predicate logic. We talked about this before. We talked about the forward chaining so-called modus ponens, where if you have A and you have a statement that says A implies B, then you can derive that B is true. Okay. There's also another way of looking at it. It's called backward chaining, and the idea is that if you want to know if B is true, and you know that A implies B, if you can prove A, then B is true. Okay. So it's a different way of using it. Okay. And this is often the way that theorem proving is done in various mathematical logic. And there is a programming language called Prolog, which that's exactly how it does its evaluation. Hands up if you've ever heard of the programming language Prolog. Yeah, cool. There was a time when that was the hottest thing in AI, and people were offered millions of dollars to go and work for companies to, actually maybe it wasn't millions, but it was probably equivalent of millions, to go and work on it. Really fashionable in the 80s. It is actually a really interestingly different programming language compared to other things, but it's not as popular as what it is, although the fundamental things that appear in Prolog are still used in lots of programming techniques. Okay, both of these forms of inference are sound, which means that everything that you can prove from them is in fact true, but neither is complete, which means there may be true things that you cannot prove with those. Okay, it's a technical point. It's not something that's a major problem. We are probably at least aware of Gödel's incompleteness theorem, even if you don't really know what it is. All axiomatic formulations of number theory contain undecidable propositions. It actually means it's incomplete. And anything that's good enough to represent arithmetic, you can come up with propositions that you cannot prove whether they're true or not because it's too hard, okay, or nobody's been able to prove it yet. We know this about all the prime numbers, various interesting conjectures there, and this is true for first order predicate logic. It's not unconnected with the fact that you can represent arithmetic in first order predicate logic, so of course this is the case. So there is more information if you want to go and look them up. You can deal with it, but so there's more information about meaning representation languages. First order predicate views of the world have been around for an awful long time, technically probably 5,000 years, but really in AI and natural language processing, round about the 80s, 90s, people started to try to see if they could convert everything, but it became unfashionable to do it. There was a company called the Sidecorp that actually tried to do it for significant domains, and they got laughed at, got lots of funding, were also successful. So all of those, I don't know which ones well, on their website they're going to say the successful ones, but they were surprisingly successful. Maybe I've got a little view there. And then people realized that once we had things like Wikipedia that were really very factual documents, they were designed to be factual, they were designed to be natural language representations of pretty much defined facts. The question is, could we actually extract first order predicate logic representations of Wikipedia? When people first started thinking about this, maybe about 10 years ago, people thought, oh my god, that's impossible, why would you ever do it? But a bunch of people have been doing it, particularly DBpedia and Freebase are really good examples of trying to get something out of Wikipedia articles automatically and semi-automatically that try to give you a database representation of the information that's actually in Wikipedia. It can't get everything because there's some ambiguity in the way people write in Wikipedia articles. There's some opinion-based things that would be hard to represent or know how to represent, but people are still actually trying to do that. And this is a pretty important bit of natural language processing. I've got a bunch of natural language. I'd like to be able to convert it into an extremely well-defined structured form. I'd like to be able to do it typically in a particular domain that you know about. Typically I want to ignore or at least not try to convert the things that cannot be converted, but the things that are actually there I'd like to be able to convert. One particular task that I'm quite aware of in this is reports by doctors on patients are often delivered in speech, and somebody has to transcribe them, and then somebody has to take the information out of the description and fill in a well-defined form, usually for insurance purposes, that has well-defined fields, that has to have very specific bits of information in it. The doctor's actually saying these things, or at least saying things that are pretty much clear and how to fill in the form, but how can you do that automatically? Well, you can think about the form as some sort of logical representation where you want the fields that are coming out of it, and how can you extract it? There's a company in Squirrel Hill that actually has made quite a lot of money in doing that. It's a fairly standard thing. Google's Knowledge Graph is actually trying to do that, and here the Read the Web NEL at CMU is actually trying to do that. Take articles and try to extract the first order predicate representations out of them. So that was a little bit leading up to this, exciting bit, if this is the exciting bit, about connecting syntax to semantics. Okay, our goal would be to take a natural language statement and convert it into a machine representation language. We're going to talk about first order predicate logic, at least to begin with. We're assuming that the sentences we're dealing with are very literal. We're not talking about opinions and metaphors. They're much harder to do, and they are absolutely common. Most sentences refer to metaphors, but there's a bunch of domains where that's not the case, and so we like to be able to do this direct mapping. This is often called semantic parsing. It's again a big topic in natural language processing. It's the sort of thing that people are trying to improve on, and all the big companies are actually working on semantic parsing and trying to get out of it. It's sometimes they call it natural language understanding, which is deeply confusing, or they might even call it natural language processing, And again, that's confusing because that's maybe everything, but they really mean semantic parsing. They're trying to get the bits of explicit information out of a piece of natural language such that they can use in a database. So I'm going to say a little bit about compositionality. This comes up to the literalness. Compositionality is that if you have a bunch of words or a bunch of things that you join together, when you put them together, okay, you get the meaning of the whole, and it's built up from the meaning of the parts. Now you might think that that's pretty common, but actually, unfortunately, in language, it's not always there. Okay, we obviously have these interesting nouns that are not compositional. Okay, a hot dog does not mean a small canine animal that has been heated up. Okay, it just doesn't mean that. I mean, it can mean that, but no, a hot dog means a sausage made out of probably not meat that's put on a bun. Okay, and it's got nothing to do with canines. Okay, a straw man is not a man made out of straw, even though it can be used to refer to that. It's a particular technique used in argument and rhetorical argument, in the same way that New York is really not a New York. Well, it is, in that there's a York in England and New York is sort of named after it, but it isn't really, because New York is named after New Amsterdam that was there before, and they just wanted to pick a less Dutch name to do it. So New York is about the city that's in New York State, and it's not really about a New and a York. Okay, if the city in Yorkshire, England, okay, ended up building some new part of the city and built a whole bunch of buildings, they could call it New York, but they probably wouldn't, because that would be so deeply confusing that they wouldn't actually do it. So there's no compositionality. And here's another compositionality thing which is quite interesting in natural language. Imagine I'm talking about a recipe, okay, and I'm going to explain to you how to make soup, okay, and what I say is you first put in the burner, you put in some water, you add in some carrots and some potatoes, and you boil them for a while, and once they're boiled, you then add the chicken into the soup. Wait, where's the soup? Where did the soup come from? I had this thing with water and carrots and potatoes in it. When did it become the soup? Okay, because why is boiled water, potatoes, and carrot soup? But it is, and that would be a perfectly reasonable thing to do. So what we're going to do is we're going to start with the parse tree, and we're going to try and build the semantics from it, and we're going to end up with first-order predicate logic. We're going to use lambda expressions, because as I hinted at, lambda expressions allow us to give us logical forms for constituents in the parse tree. So some subtree in the parse tree. So something that doesn't have all the information, I can still get a logical form for it, and it allows me to actually do some combining afterwards. So imagine we take the sentence, Noah likes expensive restaurants. Okay, so we have a parse for it. Okay, it's a perfectly reasonable parse, and we'd like to get out of that, for all x, restaurant x, expensive x implies likes Noah x. That's what we'd like. I'm defining what that is. There may be other representations of this sentence which would be reasonable, other ways to represent it in first-order predicate logic, but that's the one that I actually want, and it's a perfectly reasonable one in first-order predicate logic. So how do I go from having this parse tree to be able to get to that semantic representation? Okay, so sort of obviously, I would look at each of the words, and then I try to come up with a logical representation for each of these words that I can then care about combining things together. So I can just say Noah is the word Noah is going to be represented by the symbol N-O-A-H. That's an obvious way of dealing with proper names. They're sort of the same name, but now this is a syntactic word. Well, this is a semantic word. Okay. So for verbs like likes, what I could say is, well, it's going to have a bunch of variables in it, but ultimately it's going to give us the representation that we actually want, because it's likes that is really the thing, and we could say that likes is going to have a for all x, there's going to be some function x, the thing that is will imply likes. So something about likes is that is going to be this. We'll get a representation like that. Expensive, we can say, well, it's going to be some property on some object. We don't know what that object is, so we'll just say that that's a lambda x and expensive x. And restaurants, like expensive, it's a thing that is a restaurant, okay? So we can actually say that that's a representation of lambda x restaurant x, okay? Now, where did I get these from? The answer is, I know the answer, okay? But you know the answer now as well, because you've got it on the slide. And it's pretty generic, these answers, at least for transitive verbs, most adjectives and most nouns. That's sort of the shape of what these things would actually be. Okay. Now let's look at trying to combine some of these. Okay. So what we can do is we can label each of the nodes in our tree with these logical expressions that we got from our lookup form. What we can do is we can also amend our rules and say, what are we going to do when we're combining two constituents in a rule and joining them? So for each rule, we can write what the definition of the semantics is. So what we can say is for the NP, the semantics is whatever the semantics of the lower form of the noun. So the semantics for this NP is just the same as the semantics for that proper noun. Okay. What we can say for the semantics for an NP with an adjective followed by a form is we just say we're going to take whatever the semantics is of the adjective, and we're going to put a lambda x in it, and we're going to say or whatever is in the other one. Okay, whatever semantics is in the singular noun phrase. Okay, and so if we do that, okay, for the NP, rather simply we just get the Noah being copied up. But for here, with that rule, what we get is sort of what we're looking for. We're getting a lambda x where it's expensive x and restaurant x. These two x's are the same thing. That lambda x is conditioned over both of these x's. And so we know that whatever we're going to apply it to is going to apply to those two things. The thing has to be both expensive and a restaurant. Okay. We can have another rule that actually says for the verb phrase, we're going to take the verb itself, we're going to apply it to the NP. So we've got whatever the semantics is for that, and we're going to apply it to the whatever the semantics for the NP is. And what that gives us, with one missing step, is we're going to get lambda y, and we're going to get for all x expensive x, restaurant x, and we're also going to get likes xy out of it. There's sort of a step missing in this, because what happens here is we're going to apply this to this, and so what happens first is this f here, okay, is going to get this value, okay, on here, okay, and it's going to sit here, okay, and then we're going to take this x and apply it to here, which means we're going to get another x, so our variables have to be appropriately identified as being distinct, even though there's two things called x in there. And at the end, we're going to have a sentence goes to NP-VP, and we sort of do the same thing. We're just basically taking the verb semantics, we're applying it to the NP semantics. This is the verb semantics. We have a lambda y, and we have this big expression, and we have Noah. So what we're going to do is we're going to apply this big expression to Noah, and so we can then do lambda reduction on that, and the lambda y disappears, and this y becomes Noah. Okay, so we end up with for all x expensive x, restaurant x likes Noah x, which is what we're trying to get. Now I knew what we were trying to get, and I designed the entries in the original lexicon to do that. Okay, but they are generic, and they would work for most of transitive verbs, adjectives and nouns and proper nouns to do that. It would work. Okay. In the book, it goes from top down rather than bottom up, but it's basically the same thing. So I'm going to talk about this other thing now called quantifier scope ambiguity. So you thought that syntax was already ambiguous. I'm going to show you another way how syntax is ambiguous, okay? Because I like doing that, just to show how complex it is. And so if we have a bunch of rules like we've been talking about, and here we have this somewhat classical sentence that gets used in philosophy all the time: every man loves a woman. I don't know if it's classified as sexist nowadays. It probably is. You wouldn't select this anymore. But this has been used for at least the last 250 years to your point. So I think it's important for you to at least be aware of it. There are two interpretations of that sentence. Okay, that there is a particular woman in the world, one, that every man loves. Okay, or that for every man there is at least one woman that they love. So there's two interpretations. Okay, they can be written differently in logic. Okay, the first one is saying that there is some woman for every man, but it's not necessarily the same woman. While the second one is defining what the woman is and then talking about the love relation. Okay, and you might think this is silly, this isn't something that actually happens in the real world, we never have sentences like this, and lots of people sort of believe that these sentences are rare, but actually almost every sentence is like this. Okay, but it's not exactly like this, but it has exactly that type of ambiguity. Okay, it really is the case that every man loves a woman is ambiguous. Okay, so imagine we've got these two sentences: a seat was available for every customer, and a toll-free number was available for every customer. Okay, so if we say a seat was available for every customer, okay, how many seats do you think we have? So I'm an airline, okay, and somebody's complaining to me on the news about how I'm being cruel to all of our customers because I'm an airline, so it's clear I'm being cruel to my customers. That's what airlines do, okay? And I say a seat was available for every customer, okay? How many seats do you think I have? Do you think if I say, but a seat was available for every customer, this is it here, and all 250 customers had to sit on this seat, but this is the seat that's available for every customer? No, that's not the interpretation, okay? There's going to be a different seat for each of the customers. Now let's look at the second one. A toll-free number was available for every customer. Syntactically, it's basically the same thing. We've replaced seat with a toll-free number, okay? And if you're not old enough to know what a toll-free number is, you can look it up, but it used to be that you would use a thing called the telephone. Oh yeah, you don't know what that is. Okay, but this is not that for each customer there's a different number. That would be weird, okay? There's a single number that any of the customers can call. So in this case, the normal interpretation of is one telephone number. Well, the normal interpretation of this is as many seats as there are customers. Now, there's sort of weird things about if the customer flies twice, they don't get a different seat. But let's ignore that problem, okay? Here's two other ones. The secretary phoned up each director. How many secretaries are there? There are 12 directors. How many secretaries are there? Is it the same secretary called up each of the 12 directors? Or was it a different secretary that called up each of the directors? Or it just doesn't matter. It's just some. We don't know. It's probably that. A letter was sent to each customer. This would be really, really weird if AT&T wanted to apologise for its service and says, but a letter was sent to every customer. And somebody says, well, I didn't receive the letter. Yeah, that's because Joe still has it. He has to pass it on to Mary, who's then going to pass it on to... Yeah, no, okay? There are multiple letters, okay? But that ambiguity is actually there, and that actually appears in real life all the time. Rather interestingly, there's a bunch of people in natural language processing who come up with a wonderful answer to it, and that is, okay, we don't care. What? Surprisingly, there's a number of natural language processing problems where you don't need to disambiguate this problem. The particular place where they did this, and they ended up calling it a quasi-logical form, was in translation. And so what they discovered is, for the European languages, if you translate these into any of the European languages, don't know if that works for Basque, the ambiguity that appears in English that appears in Swedish or German or French is exactly the same. Okay, and you can just pretty much translate all of the noun phrases and the verbs and do them independently and not care about quantifier scope. Okay. However, if you do it in a language that doesn't have explicit quantifiers and doesn't do has singular plural but does mass nouns rather than count nouns, it sort of doesn't work. So all you Chinese-speaking people in the audience, think about translating these two sentences into Chinese, and you'll find that you can't really keep the same syntactic form. It doesn't work. Okay, in order to get this distinction between a single seat, multiple seats, and a single toll-free number, it just doesn't go like that. So this idea of not doing anything sort of works if you're, say, doing translation within European languages, but if you're doing it beyond European languages, it doesn't really work. Okay, I think it works in Hindi, but I'll let somebody else, and Dravidian languages in the south. But I think once you get into Chinese, Japanese, Korean, and other Southeast Asian languages, you can't really do it. So sometimes that's the sort of right thing to do, is to not care about it, but sometimes, especially if you're doing database things, you either select one of the interpretations, which actually in a particular domain might be normal, or you've got to go and ask the customer which one do they mean. Do you want one single seat shared between all of you, or do you want to have a seat each? Okay. One of the earlier lectures, and I can't remember when, I talked about categorical grammar, combinatorial categorical grammar. It's the same thing. I talked about how wonderful the syntax was. Sorry, I'm sort of a believer in this one. Where all of natural language grammar can be represented by these 5 rules. Okay, which is just so cool, because like now I don't have to write any rules. I can just use a syntax. It works for everything, and of course there's a cost for these things. Nothing is for free. It makes the representation for the words much more complex. So we've pushed the information out of the grammar rules and into the representations for the individual sentences. Okay, as it happens with CCG, it's also really wonderful for semantics. It really just works for semantics. Okay, and actually one of the things that really made it famous was it works really, really well for quantifier scope. In fact, it's one of the only grammars that sort of works without doing anything special for quantifier scope. Okay, so I'm going to give a couple of examples of how semantics works for this. So unlike the example I gave earlier with the no and the expensive restaurants, where I had to say for each rule what the semantics is going to be, I have to do this true for CCG, but I only have 5 rules, so the semantics are pretty trivial. In fact, the semantics are so generic based on this that it just becomes trivial. So when we have A/B applies to B, what we do is we just apply the semantics of this to this, we apply the semantics of this to this, or the other way around, we apply the semantics of this to this, and we're basically just looking what the slash is, and there's a direct mapping for all of these. Okay, so if we have John likes Mary, okay, we only need forward application, backward application. This is the syntactic one. I think I gave this example or something very similar before, where I said the representation of likes is this somewhat complex bracketed form, but once you see what it means, it basically means ultimately this is going to give me an S. I need 2 MPs before I can get to that S. The first one should be somewhere to my right, and the second one should be somewhere to my left. Okay, I bracket it to make sure that we can interpret this. We use forward application for likes Mary. We get a representation for likes Mary, which then is this sentence that's sort of missing an NP that's to its left. And we then use backward application and get the S. Now, for here's a more complex one. Yeah.
Well, the verb likes could just only have the subject, right? So then
correct.
You have to have a whole bunch of these rules for each word.
Correct. So as I said, you move the complexity out of the rules into the lexical entries. So you would need to have multiple entries for like. Yeah. I think I did this one before or something very similar. Syntax all comes together, but let's have a look at the semantics. Okay, so as I said for the semantics, what we really just do is sort of the same thing. We have A/B plus B, and we have semantics for A/B and semantics for B. And what we do is we get A out of it, so the A/B same as before, and we just simply apply S to T. Likewise for backward application, where we have an A/B and B appears before it, we do the same thing and S applies to T. So now we're using the colon to separate the syntactic part from the semantic part. So we say John's representation is syntactically an NP and its semantics is J. We have to have some symbol for it. While walks, okay, requires one NP to its left, and then we say lambda x walks x is the semantics for walks. The same types of representation that we were doing in the earlier one. So when we have John walks, we have the representation for John and we have the representation for walks. We apply backwards application to this, which allows us to get the S/NP and this NP to get the S. And what we get for the J, we said, is going to be S and J. So it's going to be S, which is this lambda x walks x, is going to be applied to J. So here's a little bit more. So this is what the representation is, that we fill in the information about it. The S comes for the syntax. We'll have lambda x walks x dot J, and then we apply lambda reduction on that, and we get walks J. I might be cheating and going through this and making it easier than it actually looks, but actually it is pretty easy. So writing these things is pretty easy to write. You can write the parser without really thinking much about it. It used to be a homework in one of the courses I taught sometime in the previous millennium. But coming up with the lexical entries is sort of hard. Okay, it's not very hard, but it's sort of hard. And people spend a long time worrying about how are they going to do it. Mostly they ignored it, especially when I was doing this at Edinburgh years ago. But now there's quite good statistical techniques that will try to search a space for the possible values and find out the ones that are most likely to work. And therefore this type of representation works pretty well for giving a first order predicate logic representation for things that could reasonably have it. Okay, and there's a number of people who are working in Allen Institute. Oh no, he's moved. He's now at Facebook. Luke Zottelmeyer, who worked on this in his PhD thesis and continued working on it as a representation for semantics and making it relatively easy to do. Here's another more complex example where we have John likes Mary, so the J and the M for John and Mary make it easy. For likes, we have the same S/NP forward NP, and we have lambda y lambda x for likes xy. So when we write them out with their lexical representations under them, the first thing we do is forward application, and so we do the forward application where this representation gets applied to the M, and so it gets reduced to lambda x likes x, and then we do the backwards representation to do that. So here we get the first lambda y lambda x likes xy applied to M, and it reduces to that. And for this one, we have lambda x likes xm gets applied to J, and we get likes jm out of it. As I said, deriving lexical entries is really what it's all about. If you can get the lexical entries, everything works. And so what people do is they try to hypothesize a shape of possible lexical entries. You can sort of define what that is, and you guess everything, and then you parse all your data and find out which ones you needed in order to be able to get a valid parse. You have to sort of assume that your corpus is valid sentences, but that's okay. You take it from Pentree Bank, something that probably is valid sentences. And then you find out which of your lexical entries you use the most, okay? And you either just take those, or you get rid of the ones that you never used, and then try the whole thing again, and then see if you can get a better parse out of it. This mostly works, especially for things that have literal interpretations. So things that are very clear with respect to what their meaning is, it does pretty well at giving you a logical representation. Okay? So in other words, newspaper things, not so much. You might have noticed about the newspapers in the world, they don't always tell you facts. Okay? And it's sort of reflected in that. Even if you pretend that I believe that is true in the real world, it doesn't necessarily have to be. But you can still do it for newspaper type things. Wikipedia is much better because it really is designed to be factual. Okay, but once you start going to question answers about databases, and it's pretty good. In fact, it's really good. In fact, it's better than humans in the sense that it's much more logical than what humans actually think. So all these confusable things about and or that we have, okay, that where we use and or in such a way that are actually logically confusing, okay. So if we say something like as the Titanic is going down and you have to go to the lifeboats, somebody announces that old men and women can get on the lifeboats, okay. So is that old men and women, or people who are both men and women and old? Do they have to have all those properties? So only old transgender people are allowed on the lifeboats? How do you actually interpret that? And we actually use and or pretty much randomly in human speech. It doesn't really work in the logical sense. Sometimes we use it in the logical sense, and sometimes we just mean some conjunction. Okay, and it's not always obvious. Okay, actors and directors are allowed to enter in this through this door. Do you have to be both an actor and a director to do it, or is it either of them? So actors or directors can go through there. What's the actual interpretation of it? But okay, independent of the fact that humans are really bad at logic. This is a pretty good way of trying to get logical representations out of sentences. It's not absolutely necessary to do it. Many tasks don't need as complex a representation to be able to do this. But when you are looking at trying to get a logical representation, this might be a reasonable way to do it. And I know at least 2 companies that are desperately looking for people who have some expertise in this space have independently talked to us about, do you know any people doing PhDs in this area? And the answer is, yeah, maybe. I'll have to bid on them. But this allows this fairly good mapping, and although the first thing that we talked about, this one, works fairly well, you then have to care about all the rules and find out what the form is. Well, the second one basically works pretty well too, but now you have to care about what the lexical entries are. So you get nothing for free. And finally today, I want to say a little bit about Semaphore. Semaphore is a semantic parser that was developed here at CMU by Dipanjan Das, who's now doing natural language understanding at Google, leads a group there in New York. What he and others did was they took FrameNet. Remember I talked about FrameNet on Tuesday afternoon. FrameNet gives you verbs and what their possible arguments are. And so he uses that in order to be able to get a representation for rules like these. Okay? So what he does is he goes and looks at all the verb things and tries to get the verb representations for these, and he actually tries to extract them from FrameNet. And that works pretty well if FrameNet has the verb in it and has the frame that's appropriate for that verb. And so since Dipanjan did his PhD here, which was a number of years ago, other people have actually worked on this to try to find out how to discover new frames. And Vivian Chen, who's now at National Taiwan University, was actually trying to do this to try to extract new ones from new data, and so that you could actually construct new frames from it and therefore expand Semaphore so that it can move to a new domain without a human and a linguist actually spending time working out what the various verbs are and what the various entries are. And lots of people are sort of trying to do that. So it's like, here's a framework. Humans can sort of do it if they're trained. Can we actually use the existing framework that we have, go and look at data, go and look at the distribution of data, and then make decisions about which things we add to our either rules or lexical entries, depending on whether we are standard grammar rules or categorical grammar. And the answer is yes, you can do that. You probably still need a human going in and going, no, that's stupid, we're not going to do that. But you can have some review on that, but you can get many more frames and rules put into your system much more efficiently, and your linguist is actually answering hard individual questions rather than having to parse an infinite number of sentences and trying to make decisions about every one. You only have to look at the hard cases. That allows them to actually do that. Okay, that's it for today. Are there any questions? We hope that the machine with the slides, etc., although I think the slides were going to be posted on Canvas. Nobody knows that. It should be back up this evening, and everything should be back to normal after that. Okay, thank you.